Swayam Prabha. Digital India. Educated India.
Good morning. I'm sure we all recognize our esteemed speaker for today, Professor Jim Libby, from his previous lecture on the theory of relativity. Please join me in welcoming him back for what I'm sure will be another memorable talk.
Okay, so I'm going to just spend the first 10 minutes or so saying a few final things about relativity, which are then relevant to what I'm going to say about particle physics in the remainder of the hour. So at the end of yesterday's lecture, if we were considering our two frames moving with respect to one another with some speed v, we'd found that they could be related together let me just write this as I'm going to want to. And then we have CT prime yeah. Okay. And the big change from our Galilean relativity was the fact that time is different. So the two clocks in the two frames that were synchronous when they overlap with one another will be different now in the two frames, okay? So this is the big change. And that has consequences, okay? So if we just look at the clock that's here in our prime frame, the one that's telling t prime, and we ask ourselves what would someone see if they were in the other inertial frame, the one that's not moving, so to speak. But of course, we have to be a bit careful here. Okay, so this is now fixed at the origin such that x prime is always equal to 0. So in fact, I'm interested in the inverse transformation to see what the time is in the original frame. And it's very straightforward to find the inverse transformation, because if I look at these two frames, if I'm working in S prime and it's stationary, then S is just moving with minus V with respect to it. So the inverse transformation, I'll just write the last one. All that happens is the speed changes sign. Okay? So this would be how I'd move, sorry, I've missed a prime here, or 2. This is if I was moving from the prime frame back to the original frame. And this formula allows me to understand what I was talking here. What is the time seen by S? In a moving, from a moving clock. In S prime. So if we look between some interval, t1 and t2, what I'd have is I'd have ct1 and ct2 where x0 here is just the origin, so x0 is actually equal to 0. But this would be true for the clock being anywhere in the other frame. What I would see is if I take the difference now between these two, if I have t2 minus t1, the factors of c will drop out, and what I just end up with is gamma t2 prime t1 prime. So this is one of the famous first results in relativity. What this is saying is the interval in time in the two frames is different. They're proportional to one another, but the constant of proportionality is this gamma factor, okay? And as in the gamma factor, just to remind you, is of this form. So when the speed is very slow, this is equal to 1. So everything looks like it did for Galileo and until, Einstein came up with this idea. But if something is moving fast, gamma becomes rapidly much greater than 1. So that means that the interval here is shorter in S prime than it is in S. So in the language of what we're talking about, the clock in S prime runs slow. Okay, so this is moving clocks. Run slow. So this was testable relatively quickly. They did this by flying an atomic clock around the Earth and things like this, and they found that the moving one was actually gone forward less than the one that you'd left stationary on the ground. You have to take into account some effects from gravity and acceleration, but even with that taken into account, the constant speed with which it moved relative to the other one led to an obvious difference. Now there's also a famous paradox, so to speak, about this called the twins paradox, where it means if I set off with two twins at the same age, but one of them went off on a journey away from the other one, their clock is running slow. So if they then come back together later, one will be old like me, and the other one will be young like you, okay? If the journey is long enough and the speeds are fast enough. However, from the young person's point of view, the other twin was moving off in the opposite direction. There's this symmetry, right? So why isn't that person getting old or remaining young as well? Because seems to be this asymmetry in what's happening. So the resolution of this is if they're going to come back together, at some point or another, they were in a non-inertial frame for a while. Okay? So how you would draw this is if I now have t on this axis and space here, you would have one twin just stay at home. So this would be on this line. This would be, I can say this is the blue one. And it stays here. And then the other one would have had to have done something like this to come back together at the same point in time in this frame, even if this is moving at the speed of light. And what happens at this point where they change direction is a massive acceleration, and this changes completely what's happening to the twin B here compared with the twin A. Acceleration is not part of the special theory of relativity, okay? That's related to the general theory of relativity, which I'm not talking about. But that, once you actually do the math of this in the general theory of relativity, there is absolutely no paradox whatsoever. This person will be younger, but it's all fine, okay? And because the other one's taken a completely different path, right? If you see this, they're two different paths. They cannot be equivalent to one another, okay? So, yeah, that's one famous result from relativity. There are others, which I'm just going to mention because I want to talk about particle physics as well. So the one that comes with this is length contraction. A moving stick is shorter, or a moving meter rule, I should say. Here, you make your measurements at the same time, and then you look in the moving frame and you get, it's the same logic that you apply with the clocks, except now you have a stick in the moving frame and you say what its coordinates would be in the other frame and you see it shrinks. Again, this is observable, but we have to do it with subatomic particles, which I'll come to later. We see that if we accelerate our particles very, very fast in our accelerators, they actually look like we're colliding together two pancakes in the collider, not two balls anymore. They shrink in the direction in which they're moving, okay? And of course, the fact that time is an absolute means that simultaneity is lost. So that means that two events that look the same in one frame, S, will appear at different times in the other one, just because of where they're positioned and what the times are. If they're simultaneous in one frame, they won't be simultaneous in another. So you lose the idea of simultaneous events. It becomes a frame-specific quantity. It's straightforward to show in the end. And this kind of bothers people, but it shouldn't really, okay? It just means that, you know, your clocks are different, you're measuring things differently, they're positioned differently in your two frames, so they will appear different to you depending on where you are, whether you're in inertial frame S or S prime. Then people worry about this one, thinking, couldn't you influence the future on one thing and another? But the speed limit on the universe is in all of this as well. The v has to be less than the speed of light. So that means nothing can travel faster than the speed of light. Because if I had v greater than the speed of light, this becomes a complex quantity. And it makes no sense whatsoever to be turning a real coordinate into a complex coordinate. Okay? That's not physical. Okay? You've done complex numbers, right? You know that when I have a square root of a negative number, I get this I. It's now a two-dimensional quantity in the Argand plane. It's a very different thing. Okay?
Can we cross the speed of light in other dimensions?
Other dimensions. You know more than me. We're kind of stuck in four dimensions, okay? So, no, even if, so extra dimensions are postulated, but they are not extensive dimensions. They are curled up on themselves if they exist. And in those dimensions, again, these rules will hold. This is all worked out with the theory of general relativity because they're warped curved dimensions. But it's a hard cap, okay? No one has come up with anything that transfers information superluminally, okay? You can make something appear to move faster than the speed of light. That's straightforward, but you wouldn't be able to learn anything from it in terms of getting information from A to B. Yes? Yeah, but who's seen a tachyon? It's a hypothesized quantity to do with very warped dimensions and things like this, but we have not observed a tachyon. And of course, you can find some solution to the general relativity where you might allow this, but it has not been observed. So don't worry. But, you know, Marvel continued to make money from expecting time travel and one thing and another. But unfortunately, Einstein was somewhat of a, put a limit on that, okay? Yeah, so, I don't want to talk about tachyons. I'm not really an expert on general relativity either. I just know it's an allowed solution, but we haven't actually seen the conditions where it would be viable. Yeah. So I want to keep time always multiplied by c, so I have a quantity of dimension length. Okay? Of course. But let me just do the last bit on relativity and you'll see why I want to keep the c there. Okay? So if you recall, all of this came out of this desire to have this relation in the two frames holding to be equal to 0 or whatever. And this is more general, that if I look at any difference between two sets of coordinates in the two frames, this will be a conserved quantity. So what I mean is, if I look at some delta t squared and delta r all squared, this will always be this to delta. So, you know, when I say delta r, I'm just saying from RA, RB maybe to RA, some distance between two things. So this is a sort of length preserving quantity. You have some vector in the two frames, but now it's not that the length itself is conserved like we have in rotations. It's the subtraction of the time difference squared less the length of the vector squared. That's the constant, okay? So this is our invariance now. And just as we had in 3 dimensions, is there a question, or are you solving relativity again for yourselves here? Should Einstein be worried? No, okay. So this invariance that we had with rotations with what we call a 3 vector, something with an x component, a y component, a z component. So in relativity, we also have vectors, but we make them 4 vectors, okay? And they will have an extra component, A0, at the top. And what these 4 vectors have is that A0 minus A1 squared minus A2 squared, P3 squared, is an invariant. Okay? So this is actually just a restatement of this. So in any frame moving with respect to another one, this thing is always a constant. And our position 4 vector, which usually goes by the name x mu, is CT x, y, z. Okay? So that is why I'm keeping those CTs around. It's because that's the first component of what we call a 4 vector. Okay? So why do I introduce this? One is just so that you see the extension from rotations. So the components of a 4 vector transform with the Lorentz transformations in the same way that the components of a vector transform with the rotation matrix or those cosine and sines of the 2 original components. So it's exactly the same idea. It's just more complicated because of the minus sign, right? It's not something as simple anymore as a simple length preserving thing. But it's not the only 4 vector. And this is where relativity really gets its power. I can also have a 4 momentum, which has the energy of the particle, and then it has the 3 components of momentum all multiplied by c to get the dimensions right again. That is also a 4 vector. Okay? And in this case, I'll go over here, the invariant would be e squared and that turns out to be the mass of the particle squared, all squared, multiplied by speed of light to the 4th power. Okay, that's the invariant quantity, is the rest mass of the particle. And this also leads us to have relativistic energy, which is actually written as this. So a particle with mass m moving with some speed v will have this as its energy. Okay? And you said you were all familiar with Taylor expansions. So if I have low speeds here, what you have, you'll recognize this, right? That's the kinetic energy. So the total energy is the kinetic energy plus mc squared, the rest mass energy of the particle. Okay? So the total energy now is no longer just the kinetic piece and some potential piece. You've got to worry about the mass of the particle as well. And what that means is you can also turn mass to energy and energy to mass. This is what happens in a nuclear reaction, for example. So this is where E equals mc squared comes from, really. Okay? Because it's actually E is equal to m gamma c squared. But when the particle is at rest, it's got this intrinsic energy associated with it, which is its mass times the speed of light squared. Okay? And this is where it comes from. If you are interested, you can prove this from this by thinking about what the momentum would be. So if you differentiate this with respect to the time in the rest frame of the particle, you'll end up getting this relationship, okay? Yeah. What's the problem? Correct. Yes. So if I look at the dimensions, if I multiply a momentum by a speed, an energy, yeah, so they're all energies. No, this is a 4-vector. This has got components of dimension of, I'm putting the mu there. It's confusing. In relativity, we say P is both the 3 momentum and the 4 momentum. But in principle, this has got energy components. If you don't like it this way, I can just divide this one by C. It's all the same. If any of you carry on and do physics, and you do physics to a relatively high level after your first year, you realize we cheat all the time. And we just say the speed of light is equal to 1, and energy and momentum are the same as one another dimensionally. They have dimensions of energy. And then at the very end, when you actually want to calculate something, you put back in speed of light, Planck's constant, and essentially those are the 2 basic constants that you need to get the dimensions right of everything, okay? So I admit it's a bit confusing, but don't worry about it. In the end, of course, you must have everything dimensionally correct, but as long as the components of your vector are all the same dimension, it's fine, irrespective of how you do it, okay? Essentially, they're always energy. So you work in units of energy, time, and length. Okay, so I now just have 25 minutes to introduce particle physics. I wanted to stop there. And I will come back over here. I'll erase and start again. So I'm not going to get very far, unfortunately. So particle physics pretty much began with the observation of radioactivity at the end of the 19th century, okay? And I'm assuming this is familiar to you, but I will remind you of what we mean by radioactivity. Okay, so I'd have some nucleus with a mass A and some atomic number Z, okay? Number of protons. Go to some other nucleus, plus, and this is our alpha particle, okay? So this is a radioactive decay where I have one nucleus turning into another by spitting out a helium nucleus. This is alpha decay. This was the first thing that was discovered. Then, okay, I'll come back to what else is there a little later. But then you also had this idea of a nucleus spitting out an electron and changing its number of protons by 1, and this is beta decay, yeah? And then the last one, that's least interesting in many ways, where you have nothing changing in the nucleus, but a photon being radiated out of the nucleus. That's a gamma ray, okay? And that's just the same as a spectral line from an atom or an X-ray from an atom. It's just protons and neutrons moving their position and radiating some energy. I put the star here because it means it must be an excited state of the nucleus. Anyway, this is gamma rays. So you have this alpha, beta, and gamma. Now, why it's worth mentioning this is actually examples of the 3 fundamental forces that are described in particle physics, okay? This is a strong interaction. This one is a weak interaction, and this is an electromagnetic interaction. So what particle physics is understanding these 3 forces and understanding the stuff, the nucleus, the electrons, and related objects, okay? So particle physics is just what people like to say, particle physics is the building blocks of matter and the forces between them. And that's it. That's really all we're trying to do with particle physics, is understand the different types of matter that we can find and the forces out between them. Now, what have I missed in all of this discussion so far? Gravity, correct. Why do particle physicists not care about gravity? It's very, very weak, yeah. So it's the electrical neutrality of matter that means that gravity plays a role on very large scales, okay? It's the charge of the proton and the charge of the electron exactly cancel out. Otherwise, you'd be dominated by electrostatic effects, okay? But the gravitational force, I'll write this down a bit later when I get to that part. It's about the weakness of it is so great that we never actually worry about it in experiments that we can do in our labs today. So this makes gravity very hard to understand at a particle level, okay? So we do care about it, and there are theories, but they're impossible to test in the current levels of precision that we have, okay? So with radioactivity, there was another, so, you know, this is the big picture with particle physics, but in terms of its evolution, probably the most important early experiment was Rutherford scattering. Okay? So Rutherford scattering you had a box, and you had a source of alpha particles. So you had something decaying to alphas, and then you had a thin gold film. And then these alpha particles would come in, and they would scatter through some angle theta, and you would have someone counting at different angles. And that's literally what it was. Rutherford had his students sitting in a dark room at different angles around this experiment, just counting the flashes that they saw of the alpha particles scattered through. One of the students was called Geiger, and it's no wonder then later in his career he came up with an electronic device to actually measure the clicks coming from radiation. So the Geiger counter was developed by him, which is something that measures radiation where it comes in and it accelerates and you can count electronically. Okay, so what was surprising about this is then if you plotted the distribution, it was very steeply falling. It had this distribution, proportional to this. So when theta was very small, you had lots of accounts. So that suggested that most things don't deviate at all as they go through. Okay? And at some values, some particles came straight back at you. So they were bouncing off the foil at 180 degrees. And then the explanation for this is that you have a point-like nucleus, which was a 72, essentially acted like a potential equal to 72 times the electric charge over 4 pi epsilon 0 r. And you could just see the trajectories of your particles and the probabilities of these match perfectly to having a point-like potential at the center of the atom. Okay? And when we say point-like, they couldn't see the extent of it at all, but it was very much smaller than the dimensions of the atom. We now know it's 5 orders of magnitude smaller. Okay? An atom is 10 to the minus 10 or so, maybe a bit bigger. Nucleus is 10 to the minus 15 meters across. Okay, so it's 5 times smaller. So what this means is an atom is empty space, right? This is the surprising thing from all of this. There's pretty much, most stuff is nothing. It was this entirely dense center nucleus, which was spread over this 10 to the minus 15 meter region. So what's this got to do with particle physics is that it required a different explanation of the atom. And this idea of protons and neutrons then came about very quickly, that you had these massive things 2,000 times heavier than the electron at the center of atoms, giving them most of their mass, and they were very tightly packed together. But obviously, if you have protons in a small region, that cannot be the electromagnetic force that's holding them together. So this gave rise to the idea of a nuclear force, which was very much stronger than the electromagnetic force. Okay? Now, so this had protons and neutrons. And as the 20th century developed, we learned more about the nucleus, particularly driven by the fact that people wanted to use the nucleus for power because of E equal mc squared, and then ultimately for the bomb. Okay? And people did lots of experiments and designed new things that, say, accelerated particles. Okay? So instead of just allowing an alpha to come out, you'd put it through some electric field and it'd have much greater energy by the time it hit the target. And what people found with these accelerated particles is you found more and more new particles, which were heavier, and then they decayed into other things, okay? So these were called things like pions, kaons, sigmas, etc., etc. And it was just, it was like, you know, there was no rhyme or reason to these particles. People were looking for things, patterns or whatever, but it was very hard to understand where they were all coming from. But there were some other puzzles as well. One is antimatter, because someone asked me about this. So you've probably done a little bit of quantum mechanics. De Broglie wavelength, anyone? Yeah? So you will have learned there's this particle wave duality, we'll say. In quantum mechanics. And what people found when they coupled up the ideas of quantum mechanics with the theory of special relativity is that you had to alter your view of what an electron was, okay? So relativistic quantum mechanics required spin half particles, okay? So you may have heard of spin when you're doing your chemistry and you're filling levels and all of this stuff. It's requiring that you have spin up and spin down, and then you fill one level, and you've got different angular momentum, you've got the spins, so on and so forth. So that required that the electrons was spin a half, but it also meant you could have an antimatter version of it, because there were 4 degrees of freedom in this. Which is called the E plus or positron. Okay, so the theory was completely symmetric. It said that I would always produce a positron along with an electron. Okay, so this is this pair production mechanism. If I have a photon with an energy greater than twice the mass of the electron, c squared. If I put it into a material, I can see an electron and a positron produce. Okay? This has to be done in a material because of conservation of momentum and energy and things, but this was observed. And what it showed is that if I got an electron produced, I would also have a positron. There was no way of creating or destroying uneven amounts. So this goes back to someone's question yesterday about matter and antimatter asymmetry. But we do know that our theory ultimately does require there be some difference between matter and antimatter. Otherwise, you wouldn't have this matter-dominated universe that we see today. So, yeah, this is an antimatter particle. And then if I run this backwards, when I have a positron and an electron come together, that's going to just annihilate to create a photon. Okay? Yeah. Yeah, so yeah, sorry, for me, time always runs from your left to right, yeah? I don't normally. Sometimes in particle physics, people do it the other way. You just have to define which way you go. No. This is a myth. Okay, it was a way that people interpreted antimatter originally about trying to move it backwards in time. But we do experiments with antimatter. It very much moves forward in time, okay? It's just a technicality in how you actually define everything to say it's moving backwards. And in the modern way of thinking, something called the Feynman-Stuckelberg interpretation, you shouldn't really think of it in terms of it going backwards in time, okay? Because it doesn't make any sense, right? We can't do experiments that way. Yeah, so I've got about 10 minutes left. So yeah, so there's these various mysteries. There's antimatter. There's all this zoo of particles. And what someone called Murray Gell-Mann, realized is he could make sense of this zoo of particles by postulating that the proton and the neutron were not fundamental particles, that they themselves had structure inside them, okay? So this is the whole inward bound thing. Okay. And what these quarks were, so an up quark, very light, about the same as an electron, a little bit heavier. It was also had a charge, but the charge was plus 2/3 of the electric charge, okay? And then the down quark, also approximately, and these are also spin-1/2 particles, like electrons, okay? And then there was this, with this you could say a proton, don't worry too much about my notation, is summing together 3 quarks, 2 up and 1 down. So that will be 4/3 less 1/3 to give me +1, positive charge of the proton. And then the neutron is 2 down quarks and 1 up quark. So the 2 down quarks are then -1/3, cancel out the +2/3 and give you a neutral particle, okay? And what made this particularly successful was there was also a 3rd quark called, which was called strange. The strange quark, because it obviously wasn't fitting, it wasn't necessary. It wasn't part of the nuclear, the nuclear particles, the neutron and the proton, but it was there and it was describing all these other particles, or some of them at least. And that has a mass which is much heavier, around 100 MeV, and also had -1/3 electric charge. Of course, it was spin-1/2. Okay. And with this, they could actually label all the particles. So we'd have the proton and the neutron, then we'd have a series of states which are and then we have USS and CSS over here. And there were 2 possibilities where you had these sets of quarks. These were called the sigmas. So sigma plus, sigma 0, sigma minus, and there was two neutral ones, different masses, and then there were these psi's down here. So all of these particles have been observed, and these ones were getting heavier as you went down here. And that was the presence of this heavy, strange quark, making them heavier. And he could describe all of this. And he could also then describe combinations of a quark, and this thing with the bar over the top is the antimatter down quark. Okay? So just like for a positron and an electron, if I'm producing a pair of quarks from a photon, which I can do, it's got electric charge, so it couples just in the same way. Well, strength is a little lower, but I can produce a pair. One is a matter particle, the other is an antimatter particle. And again, we see all of this in the laboratory. So I won't go on and describe further this classification. It's called the eightfold way, and it made sense of this these particles that have been discovered. All right. So I just now want to go back, or maybe, yeah. And the others. So I'm doing this historically at the moment. Initially, people, even Gell-Mann was a little reticent to say that the quark hypothesis was correct. Okay? So this 3 quarks was ambitious, but then some people postulated a 4th quark, and that was discovered in 1974. But until that time, jury was still out on the quark model. Okay? But then people started to believe it. Okay? So I will mention everything in a minute, but I just want to say one more thing about these bound states of quarks. They're being held together by that strong nuclear force. Okay? It's got nothing to do with electric charge, so there's a new type of charge involved. And it actually means that there are 3 different types of quark. So if I write an up quark, I need to give it a subscript to say whether it's a red one, a blue one, or a green one. Obviously, they are not colored, right? They are not really colored objects because their size is so small that any wavelength associated with them would be nothing to do with the visible. But how the quantum theory that describes particles, and particularly the strong interaction, means that there are 3 different types of charges. They are all the same strength, but they are different to one another. So there's a red charge, a blue charge, and a green charge of the strong force. And that's what's holding together the different particles that we see. So when we have, say, a proton, we have 1 red quark, 1 blue quark, and permutations. So this red, blue, and green combination together, this is a very complicated set of charges. It's not like electromagnetism anymore. This is considered colorless, right? Just as you know you get white light when you put together the 3 primary colors, this was the idea here, that you got sort of 0 net color charge. And those pions and things, similarly, my pi plus that would have negative color charge or anti-color charge, okay? Just in the same way that the positron has positive charge compared with the electron's negative charge, this would have anti-redness compared with redness. And this cancels out to give zero net color. So these bound states of quarks were all found to have zero net color, and hence they are observable. But we can never see a quark by itself as a result of this. Quarks are confined because they have net color, and when you try and move them apart from one another, it takes so much energy you create colorless objects, you make other particles. So it's very, very different, and this is why the strong force is short range. Okay? The strong force is very different to electromagnetism in terms of how we set it up, and as a result, it becomes short range because of this inability for us to extract a single quark from a particle. So this is something called confinement. And I'm sorry, I can't tell you too much about this because this is really in the depths of quantum field theory as to why this happens. So when we write down a field theory for both electromagnetism and the strong interaction, there's a difference in how you set up the forces, and this leads to confinement. Okay, I'm really out of time here. So just to say, and just maybe to finish, what we know, summarize what we know now. So all of this expanded okay. So what we found is there were 3 replicants of the quarks. So all of these ones along the top have plus 2/3 of the electric charge. All these along the bottoms have minus 1/3. This is the charm quark that someone just mentioned, which partners with the strange quark. This was discovered in the 1970s. Then to describe the difference between matter and antimatter, 2 Japanese gentlemen, Kobayashi and Masukawa, predicted there would be a 3rd generation even before we'd seen the charm quark. So people thought they were crazy. But they turned out to be absolutely correct, that there was a 3rd generation. And this is, we call this the top and the bottom. Originally Truth and Beauty, which are much nicer names, and we still call the B quark Beauty at times. Okay? So the thing that's changing along here is mass. The top quark is 175 GeV. The up quark and down quark is 1 MeV over c squared in mass. So it's spanning 5 orders of magnitude in terms of the mass scale going from this to this. This we do not understand, okay? And then we also have 3 versions of electrons. And they have a partner called the neutrino, which is the extra thing produced in beta decay, which is required to conserve angular momentum and linear momentum in the decay. And these have electric charge minus and 0. Okay? So again, we have masses going up. This is 511 kilo electron volts over c squared. This is 1.77 GeV over c squared. So it's not quite as much as the quarks, but there is a difference in mass as we go along. These are the building blocks. This is what I said in the original statement of particle physics. This is what we say matter can be made of. But all these things of higher mass are unstable. So they decay like we have in the weak interaction. In beta decay, we have a down quark turning to an up quark. Similarly, we can have a charm quark turning to a down quark. And these things all decay away. Similarly, the muon will decay to an electron and to neutrinos. So these are short-lived particles, and we've measured all of these things. And I can't tell you why we have 3 sets of these, why we don't have 4, but we certainly appear to only have that. And then to the side of this, we have the forces. So we have the photon, which is what is is what we say is mediating the electromagnetic force. So every time two charges interact with one another, they're actually exchanging photons between them, okay? And then the thing that does the strong force is called a gluon. It's also massless, like the photon, but it couples to itself, and that's one of the reasons we have this confinement, okay? Whereas the photon can't color to itself. So the gluons are actually 8 of them, and they are bicolored. So there'll be things like red, blue bar, etc., etc. Then we have something called the W plus minus and the Z. These are heavy, 90 GeV, and this is the weak force. Okay? And that's what happens inside beta decay as a W is radiated from one of the quarks. And this weak interaction is, I had to just get my numbers. Yeah, this is 10 to the minus 13. If this one is 1, this is 10 to the minus 2. Okay, so this is the strength. Sorry, it's not drawn out very well. Strongest is 100 times more than electromagnetism. And this is 13 of orders of magnitude weaker than the strong interaction. So it happens very rarely. The consequences are very small and not very well observed normally. But this is a special force, what I'm studying, actually, and it has many interesting properties, which I'd have to come back to give another lecture on. But I'll give up now. Okay? So yeah, I should stop there at 10 o'clock. I can take some questions. So because matter and antimatter are made together, it's very easy to produce antimatter in the lab. You just have a high enough energy photon or a beam of particles. You'll get a spray of particles, half of which are matter and half of which are antimatter. So if you make enough antiprotons, you can select them using magnetic fields. You can then slow them down. And as long as they don't interact with anything, you can then put a positron in to make antihydrogen. Okay? So you just bring them together and they will form hydrogen. Okay? And this is how they've done it. Of course, they have a low yield. There are millions and millions of attempts, but a few of them do come out. And then they measure the spectrum of hydrogen and antihydrogen to see if there's any difference. So far, they're identical to one another. Okay? But yeah, once you make particles, you can manipulate them. You do everything in a vacuum. It doesn't interact with anything else, doesn't annihilate. So it's easy enough to get a few antimatter particles at a time. Okay?
Is it true that massless body can travel beyond the speed of light?
No. Massless particles travel at the speed of light. Yeah? So the other nearly massless particle in the standard model, it does have a tiny mass, a neutrino. It's found to travel pretty much at the speed of light. Okay? Gluons would also propagate at the speed of light, but they don't go very fast, so we can't be sure of that. But how the equations of special relativity work means that their speed will have to be exactly equal to the speed of light. Okay?
So, but is it true that if a body travels at or beyond faster than the speed of light, then it can travel the reverse line?
Nope. Not true. So the theory of relativity is time invariant. I can reverse time and it looks exactly the same. So there's nothing special one way or the other. You know, it's well, the arrow of time is an interesting question in itself. Okay, but essentially the theory, you can't because something goes fast, you can't reverse the speed of. You can't reverse time. Okay. This first, and then you. I think they want to start the next lecture though. Yes, sorry. Yeah. Neutrons do decay. So if if you take a neutron out of a nucleus, it's got a lifetime of 13 minutes, roughly, and then it will decay to a proton and an electron and a neutrino. So proton has nothing to decay to because it's lighter than the neutron. So as far as we know, the proton is stable, but many non-standard model theories think the proton should be unstable, but its lifetime has to be significantly greater than 13 billion years, which is the lifetime of the universe. Otherwise, we wouldn't be here. Yeah? All right. So it's possible, and it's a very active area of research is to try and see proton decay. Okay? Sorry? Exotic matter. Yes, but it doesn't live very long. Well, you know, what do you consider exotic matter? Oh no, that's too exotic. Negative mass, you know, again, an antiparticle has regular mass, it has opposite electric charge, okay? It still has energy, mass, they're all the same, but negative mass is not a concept in general relativity either, right? So we haven't observed anything like that. We've observed exotic combinations of quarks. So we see objects made of beauty quarks and charm quarks, and some people refer to these as exotic. And we've seen combinations of 4 quarks, 5 quarks, 6 quarks, some people think, baryon, dibaryons. So yeah, it depends what you call exotic, okay? Yeah. Yeah, so okay. In the early universe, okay, all the energy of the universe was confined to a very small region, okay? And that means it was very hot. But what that means is that you were creating and annihilating pairs of particles all the time, okay? It was so dense that there would be an electron and a positron, it would annihilate, go to a photon, then become electron and positron again. Of course, it was more complicated because this was also going to all the different types of quarks. It was going to W. It was going, yeah, that would do. The charged particles is what this would go to. But I'd have other reactions involving gluons and Z0s and this, that, and the other. And these things were just going back and forward with one another. They're in equilibrium, okay? And everything is even. At some point, there had to be a balance goes between them, and suddenly I'd start getting more of one type and another. And I know that if I have a beauty quark I can get this to be, so not U bar, that doesn't work, D bar. This I can get out of equilibrium in the standard model because there's a, not quite, I need 2 of these interfering with one another, but I can do this. And that would give me CP violation or the difference between matter and antimatter. But it's tiny. It does not explain what we see in the universe. This could be, doesn't happen. But it's a mystery of the standard model as to where all the matter, antimatter went, why we live with the matter now. The other mysteries are dark matter. So everything I've described is only 5% of the universe. Yes? Yeah, I think there was another, maybe just follow up on this one and then this should be the last one, I think, after that. Bit louder?
You said it was a mystery, right? What happened to them?
Yeah, we don't know. So the early universe was really, really hot. So there was lots of potential for there to be particles produced that are very, very heavy that we are yet to observe. Okay? In our experiments, because we've not created those very large energies. One of these possibilities is a heavy version of the neutrino. Okay? That seems a likely possibility of where there could have been very large matter-antimatter asymmetry and could then have driven the whole thing. It's a process called leptogenesis, and it seems plausible, okay, as to have generated the whole thing. But it's also possible there's a completely new set of particles we haven't even thought of that have large matter-antimatter asymmetry, okay? So it's open. It's an open question. Leptons are this lot. Sorry. These are quarks. Hadrons are composites of quarks and baryons. So hadrons are split then into mesons and baryons. Baryons are the 3 quarks. Mesons are the quark-antiquark. Yeah, all of these are bosons. This is spin 1, spin 1, spin 1. Ah. Oh. So the Higgs boson is required to give mass to the W and Z. Okay? So one has to do a process which seems very ad hoc, which is called spontaneous symmetry breaking, where you say there is suddenly a preferential direction in a potential that describes the Higgs particle. And with that breaking, that symmetry breaking, I can get the masses of the other particles. This is the Higgs mechanism. The Higgs boson is a consequence of that. So Higgs predicted this in the 1960s, and some people didn't think he was right. But then at CERN in the early 2011, they actually found the Higgs exactly where we thought it would be. So the Higgs is also in there in the standard model, and it's required to give masses, to make these things massive compared with the other force carriers which are all massless. Okay? It's at the end of the 5th year of the dual degree students, I lecture and tell them all about spontaneous symmetry breaking. So you have to do quite a lot to get there, okay? Okay. I think I should stop there, I think. Okay, last question until someone comes with another one. Yeah? Standard model doesn't break down. So there's, I guess you've seen like a phase diagram for liquid, solids, and gas where you have pressure and temperature. So there's a similar phase diagram for quark matter. And this matter you talk about is cold because it's in a neutron star. It doesn't have much kinetic energy, but it's highly compressed. And that's a little bit unexplored in terms of our theory of the strong interaction. But the strong interaction does predict what should happen. You'll just end up no longer with baryons as we know them. We just end up with quark-like matter that's very compressed. So it is interesting. And people need to get more information about neutron stars, which are hard because they don't radiate, so you can't learn that much about them. But people think there would be this kind of new state, but it's not new physics. It's just the strong interaction in extreme pressure, low temperature. Yeah? So, yeah, while we're setting up, I should start erasing. Yeah, tell me, I'm listening. Yeah.
Then this downward and opposite material.
Sorry, the last bit I didn't catch.
Downward is by getting electron. Then this downward and the opposite material from electron and upward.
No. It's So I erase, but what really happens is the down turns to an up quark. This W boson is radiated like a photon from it, but it's massive, so it decays very quickly. And this goes to the electron and the antineutrino. Okay, so it's not that this is a bound state, the down quark's going to an up and an electron. There's this intermediate W, and the W then decays to the electron and the neutrino. And we've observed all of this, all right? So it's a different, slightly different process. Okay? Okay.
How was the first particles like quarks and electrons formed in the early universe?
But just because it's, if I take energy, I can make matter. This is E equal mc squared. So there was enough energy, either through photons or gluons or anything. The energy density was very high. That just turned it into matter. Okay? It was just a possibility, a quantum mechanical possibility. Yeah? How the Big Bang happened and what was the initial conditions, okay, I can't tell you exactly. But I know a few 10 to the minus 13 seconds afterwards, I know that it was a heat bath with the particles behaving. We know this much.
Thank you, sir, for opening the doors to relativity and particle physics, from deriving the infamous equation E is equal to mc square to introducing us to the non-fundamentality of protons and neutrons. This lecture truly delved into some of the most interesting concepts of physics and mathematics. I'm sure your talk has left us with a sense of wonder about the complexity and brilliance of even the smallest physical particles. Thank you once again for your time and effort.